Okay, so those that are just joining, thanks again for joining. So we're starting this warm up. So basically, if I give you a data set and then I want you to estimate the points in between the set, what's one method that you can do to do this? Yeah, so you're gonna interpolate in between the points. So you can assume linearity and then derive the equation for linear interpolation. So where does this equation come from? So you're defining your points, you define your slope, and then you define the equation. Basically, this is y equals mx plus b. And then you try to interpolate in between the values. So now I gave you the equation. Now see if you can use this equation to estimate f of 1.3 and t of 5. Okay, so in the first one, we have f of 1.3. So that means given f and t, what would be a function of what? So first we'd have f as a function of f is a function of t, right? F is a function of t. So the input variable, this is the independent variable, and then f would be the dependent variable. So I look at 1.3 and I want to interpolate between, let's say 1 and 2, right? So I'm trying to get a point in between 1 and 2 such that it's in the linear section between 1 and 4. So I plug in the equation. I have f of 1 plus x minus 1 over 2 minus 1, where f1 is going to be 1 and y2 is going to be 4. Okay, so you plug in the equation, that's what you get, 1.9. See if that's what you get. See if you agree with these numbers. The important thing to understand is you have to think about what's your y2 and your y1 minus your x2 and your x1. And then this is going to be your known value. So that's your known. That's the point you're trying to estimate at. And then this is your unknown. Okay, so similarly, for this one, now we need t as a function of f. So we need t T as a function of f. So now the input is going to be f. And now we're trying to look between these 2 points. So technically it's nonlinear at this point, but we're still going to try to estimate it, assuming linearity. Okay, so you're kind of doing the same thing. T at 5, you plug in f equals 5 right here into your x. And then you calculate your y. Okay. So try to see if these numbers make sense. See what you're interpolating. So these equations actually aren't in your book. These are from other intro classes. But the name of the game is going to be the same pretty much for this entire lecture. We're just going to have some data series and then try to interpolate, try to get a function. And then interpolate just means you want to get something in between those points. Okay. So any questions about the warm-up? That's basically what we're going to be doing today. All right. So we've covered a lot so far, right? Today we're covering chapter 6. We're skipping chapter 5, but I encourage you to check it out on your free time. Maybe even after this class, even after you finish this class, you can definitely check out eigenvalues and eigenvectors. Raise your hand if you've learned about eigenvalues. Some of you, a little bit. Cool. I didn't learn about them until grad school, but they can be very useful, very interesting. But today we're doing chapter 6, which is basically curve fitting and interpolation. So this has lots and lots of applications. And I think basically after today's lecture, we still need chapter 8, 9, and 10. But in my opinion, basically, this is the bulk of the course. I think after today, you'll be more than ready for your projects. You can use any of these methods that we covered so far in chapter 3, chapter 4, and then chapter 6. I think y'all be totally ready for your projects and your classes. Again, there's some other stuff that we need to cover with calculus, differentiation, integration, and differential equations, like modeling some multivariate functions. But for your project, and basically for most of the methods in the rest of your classes, for the entire degree, this is pretty much it. All we need is curve fitting, and then that's pretty much what you're going to be using for most, I would say most of the degree. So that's pretty exciting until you do some more diffie-qs and then you need some more functions. But it's pretty exciting because in less than 1 hour, we'll be on our way to be almost finishing. Okay. So again, we're doing curve fitting. So basically what that entails, first, we're going to start with a linear equation. So applying what we just learned about linear interpolation, how can we get a linear equation and then fit the data? So basically, I'm going to give you some data, and then we want to describe it with a line. And then what if we have some nonlinear data? Well, we have to figure out a method to linearize this function and then convert it into a linear equation, basically. And then similarly, we'll have higher order polynomials. Then after that, we'll be interpolating using a single polynomial. This is called Lagrange polynomials. And then also Newton's polynomials. And then I'll give you a brief introduction to spline interpolation. So my guess, this is just a tip. We're gonna try to cover as much as we can. And then I'll just give you a brief introduction to spline interpolation. So I really want for your homework to go over spline, linear splines and cubic splines. So remind me when's your quiz? You have the midterm and then you have also a quiz. The next week? Okay. My guess is that you're gonna get tested on like theory. So I recommend you study these three for your quiz, and then get some points, because you'll definitely get tested on for your final as well. Yeah, but today we're gonna start simple. We're gonna start with just a linear curve fitting. Okay. All right. So what's the main idea? Basically, if I give you a set of linearly correlated data, if I give you some x values, I'll give you some y, we want to interpolate the linear function that basically fits that data. So that's called curve fitting. And then also, if we have some nonlinear set of data, how do we linearize the function to get a linear model that fits that? And then finally, can we obtain a polynomial function that interpolates this data, which is going to be Lagrange and Newton polynomials? And then using these polynomial functions, how do we interpolate the lines between the points? So that's going to be spline interpolation. So this chapter is pretty nice because this first objective fits into the second objective, and then the second into the third. And then finally, spline interpolation is basically covering it all in one. So each objective builds on the last. So it can be a little bit tough, but once we do the first line, then we can do it for all the polynomial functions. Okay, so let's just get started with curve fitting. So again, we kind of briefly went over this last time. We have some data points, and then we want to obtain the line y equals mx plus b. So what better way than to do this with an example? Okay, everyone start by copying down this data. So I give you some x's, I give you some y's. Hopefully y'all can read that. Okay. Great. Okay, so as you all know, I do research, right? My research is in water. So sometimes we need to do a calibration curve. So who can tell me what is a calibration curve? Calibration curve. So I have nitrate concentration. So what is nitrate? You have the concentration of the nitrate ion, right? And the units are in millimolar. And then I have the absorbance. So who can tell me an equation that relates the absorbance as a function of concentration? Yeah, Beer's law. Very good. So we have absorbance. The absorbance. Yeah, epsilon times the, I'm going to write path length first, times the concentration. Good. So we have the absorbance. And then we have the concentration. Okay, so all we have to do is figure out what's the input, what's the output variable. Okay, so we have the input variable is the nitrate concentration, and then absorbance is the output. So, I'm a chemie, so I have to think like with the box. So this is the input and this is the output. So we have absorption, and the input is concentration and the output is the absorbance. Okay. So why do we need a calibration curve? Because the instrument basically detects absorbance, and then I want to interpolate. So just like the warm up, suppose I have some absorbance within this data range, then I want to interpolate. So if I'm being totally honest, I just use Excel to do all this for me. But today we're going to learn how to do it on MATLAB, and Excel uses the same features, the same functions to do it, what we're going to learn today. So the name of the game is we want to calculate the slope. So how do we do that? What's going to be our method for getting this slope? Say again. Okay. So we're going to be learning something called, we're going to try to derive the linear least squares regression. Linear least squares regression. Least squares. So I'm going to give you some function. Let's call it E. And E is a function of the slope. The book calls it A1 and A0. So do we want to use M and B, or do we want to use A1 and A0? So raise your hand if you want to use the book way. Raise your hand if you want to do MX plus B way. Doesn't matter. I'm going to do MX plus B. So you want a function of M and B. So this is a multivariable function. Multivariable function. So what does that mean? You have multiple inputs, right? Multiple inputs and one output. So our goal is to minimize this function. So we're going to define this function as the sum of the square of the residuals. So Ri is the residuals. So what is a residual? Just think of residual as like your delta y. Just think of this as your delta y. And we want to minimize this function. So delta y, that's just going to be the sum of yi so yi minus mxi plus b. And this is squared. Okay? So our goal is to minimize this. So how do we minimize that? Yeah, we're going to take the partial derivative with respect to the slope, set it equal to 0, and the partial derivative with respect to the intercept, set it equal to 0. Okay, so if we do that, so okay, how do we do that? So what's the partial derivative of this function with respect to slope? Good. So we just treat everything else as a constant. We bring down the 2, just like single variable. We differentiate that. 2yi minus. I'm going to distribute that negative. And then we multiply by xi, right? That's equal to 0. Similarly, we're just going to have the sum. So now I'm going to take the partial derivative with respect to b. Yeah, you're right. There's a negative there. Thank you, Takumi. There is a negative. And then, so that one's going to be similar. It's just going to be the summation from yi minus xi minus b. Okay, and set it equal to 0. So what your book does, which is very useful, so we're just going to define some functions. So let the summation from I equals 1 to n of, let's see, this would be just b xi xib. So this is just simply you're adding up all the terms, right? So in this case, this is just going to be n times b. This is just n times b. So what is n? What is n? Yeah, it's just the number of points. In this case, 1, 2, 3, 4, 5, 6, 7. We have n equals 7. Let's say n equals 7. Okay. And then we have let summation of xi from I equals 1 to n. So do we understand what this equation means? So it just means simply just take your x values and you add them up all together, right? Like everyone understands that? And then similarly, we'll have xi, yi is going to be the summation of x, sx, y. So first, now with this equation, the first step is to multiply the values one at a time. And then you add those all together, okay? I equals 1 to n. xi squared, sxx, and yi, sy. So raise your hand if you have any confusions about these equations. These are just definitions. These aren't anything fancy. So now we have a system of equations. How can we solve the system? I'm going to rewrite it just to make sure we're on the same page. So we have this system of equations. I'm going to do a little bit of rearranging. It's going to look something like sxx and okay, so here's our system of equations. So our goal is to find, what's our goal again? We solve for the slope and the intercept, right? So how do we solve the system? Solve for which one? Sx. So solve for this. And then you want to plug it into here. Okay. I haven't tried that. I'm not sure if that's going to cancel anything out though. So you can solve for one equation as a function of 1, plug it into the other equation, or you can just simply do Gauss elimination. Gauss elimination. Okay, so if you do that, we'll have the functions. So you're gonna get Sxxy minus n times Sxy, and then Sx squared. And then B, need to check what B is real quick. Let's see, NSXY, and then this would be SX. Like this, right? And this one's squared. So these are our equations. So now these are all known data points. We can plug that in, and then finally we'll have the equation f of x equals mx plus b. Simple, right? Hopefully. So we have our data series, we have our function, we have our m and our b. So all we have to do is input this into MATLAB, try to obtain the function as a function of mx plus b, and then we can code up the solution, and then hopefully try to calculate the epsilon and the path length, is slope. Okay. So, any questions before we move on? Okay, so here's our data series. This is either going to be like from your lab. This is going to be from some database. So you collect your data series. You can even import it from Excel. And then, first thing I want to do is plot it. Okay, so here's our data, and we want to plot the function. So basically all we have to do is try to program each of the previous equations. Okay, so hopefully you wrote those down. So basically I'm going to define sum of x equals sum of x, sum of y equals the sum of y, sum of xy move the first page up. Okay, all right, I'll do that, Sandra. Okay, any questions about this? You all agree? Hopefully there's no typos or anything like that. And then I can just simply define my slope minus n times sxy, right? I'm just inputting the equations that we just derived. Sx squared. Let's see. Let's run that. I need to say what is x. So this is the nitrate, and then y is the absorbance. Nitrate concentration. So what is n again? N can just be the length of the function, the number of data points. Okay. let's see, I think this would be negative. I forgot that one that Takumi told us about. That's the slope. Okay. All right. And then what is my intercept? S x times sy, s times sx, sx squared. I think that should be good, pretty much for the most part. So the slope is really small. So therefore, I can plot, if I type hold on, so yeah. Sorry if I'm not really thinking out loud, but basically we have the data series, right? I gave you this, I gave you this. This is gonna allow me to plot both functions at the same plot. And then I'm just simply typing up, I'm not doing any code, I'm just transcribing. I'm just typing up the equations. So any questions about these? So this gave me the slope. So what I can do, which is the really useful part, basically I can just define the anonymous function. Let's call it just y as a function of x, right? As an anonymous function. And that's going to be mx plus b. So if I plot that together, I can see, basically I can see if I'm correct. Let's see if I made any typos. What did that say? Line 29. This is an at x, not f of x, at x plus b. F should be f, like this. Okay, no typos. And there we go. So the line fits the data. All right, you can see that, right? Perfect. So this is a really good way to check. Once you have your code, you want to plot it visually and see if it makes sense. So we're minimizing, we obtain these equations by minimizing the square of the residuals. Okay. And then we can plot the data. In this case, it's a line. So I think it fits quite nicely. Perhaps the second step would be to calculate the r squared value. I'll let you guys do that for your lab. So what does the r squared tell you? The residuals, if I have an r squared of something close to 0, is that good or bad? If the r squared is say 0.9 or no, 0.1. Yeah, it's not good. It tells you it's non-linear, right? Let's write this down. Let's write this down. This is kind of the take-home message. Okay. Okay. So we plotted the data. We have absorbance as a function of nitrate concentration, right? And then here's the data. So we said that absorbance is equal to epsilon path length times concentration. So the slope is, what did we get? 0.0739. 0.0739, right? So for your lab or for your homework, I want you to calculate the R squared. So suppose the R squared tells you about linearity. Box this down, write this down. So the R squared ranges from what to what? Yeah, 0 to 1, good. It's gonna range from 0 to 1. So if you have something like 0.001, is that linear or nonlinear? Yeah. So if it's close to 0, that's going to be a nonlinear. If it's close to 1, say my R squared is 0.999. That's going to be very linear, right? It's going to fit right on the line. So this is going to be linear. So this is your check. I want y'all to keep in mind for this class and then for the next year or two for your data, for your labs. Your goal is to minimize your error. So you want to have your R squared close to 1. Okay? Equals 1, linear, or close to 1, linear. It's close to 0, it's non-linear. All right? So someone asked to see this page again. I guess it was this page. I'll be sure to put it up during the lab. So to recap, I gave you some data sets. I gave you a model. So here's our model. So in this case, this might come from your chemistry classes. You might learn about models in your engineering classes. And then we try to model the data using the mathematics. We obtain a function. We derive the equations. We derived the slope and the b. We use MATLAB to plot the data to see if that worked. And then we tested the linearity. So for the rest of the chapter, that's exactly the same. We're not doing anything different. We're just getting more and more complicated models. So first we have linear models, and then we'll have other types of models. Okay, any questions about that? Pretty much good, right?
Andrew?
Yes.
I don't know if the Zoom class can't really see the what's on. It looks like it's funky. I think it's funky or something. I don't know, maybe an effect.
How long has it been like that, Cassandra? Like not that long, or like the whole lecture?
Oh, there you go. It went back to normal.
It's back? Okay. Yeah. I didn't say anything really new. We just recapped. So we have the data series. Okay. Yeah. Just recap. So we have the data, the equation to model the data, the mathematics to derive the slope and the intercept. We did this on MATLAB, and then we tested the linearity. The main thing I want you to keep in mind is the R squared, the R, the residual. This is the main thing, residual. Because we're using this concept for lines, and then we'll use it for polynomial functions. Okay? So last time, R squared close to 0, bad. R squared close to 1, good. All right. Okay. Thanks for clearing that up. Hopefully you can see my screen. Yeah, let's continue with the lecture. So how much time do we have? 15 minutes. All right. So we're going to quickly peruse the rest of it. So again, these are the equations. You can write down these, or I can show my notes after the lecture. So yeah, that's lines. And then if we have some nonlinear forms, then we can approximate them, we can linearize them. So does anyone have any questions about how to linearize these? So if I have a nonlinear function, sometimes we can approximate them with lines. Values for linear least squares regression. No questions about these? Good. So the next thing is going to be curve fitting with quadratic and higher order polynomials, but really it's no different. So we're just trying to minimize the error again. But in general, we're going to have an nth order polynomial. So m is going to be smaller than n minus 1. So in reality, I personally haven't seen much application of polynomials because you can have technically a very large number of data points, right? And have up to that number of that degree of polynomial. So if you have a line like this, first degree polynomial, yes, you can get up to the 10th degree, but why would you make that function more and more complicated? Might as well just approximate it with a simple function. So we're not going to cover this one too much. Interpolation using a single polynomial. Rather, we're going to focus on this, and let's focus on Lagrange polynomials. So Lagrange polynomials, we're trying to obtain some lower order polynomials. And then again, your Excel or your MATLAB or your online computers, they can do all this for you, but the purpose is to learn where this comes from. So does this equation look familiar? What equation is this? It's basically just y equals mx plus b. It's the interpolation between two data points, which we covered in the warm-up. So if you want to know where this equation comes from, just review the warm-up. So if I give you some data points again, we want to interpolate the point in between. And then now the goal is not to obtain the value, we want the actual function. So pay attention to this. This is first order. Okay, so now we're going to second order. So it gets very, very complex very quickly. Well, all you're doing is you're multiplying the difference of each of those terms times the term at that y value. So hopefully you can see the pattern. This is just a value of pattern recognition, just a function of pattern recognition. So once we have second order, which will fit the data even better, we can just have it for any order. So in general, we're just multiplying this Lagrange function. So Lagrange function is nothing else other than, so let's make sure we understand this equation. So your x is your kind of like, it's like your unknown, right? This is what you want to interpolate. But you do know these. So you know your xj, you know your xi. So what does this pi mean? So what is sigma? Let's talk about sigma first. What does sigma mean? Yeah. So this is the sum. So this is not the same as series. So why isn't it? Is this a series? Or why is it not a series? This is not infinity, right? It's not an infinite series. So it's not an integral, it's not an infinite series. It's just the sum of each of those terms, right? What about this? What is the piece, the pi? Yes. Yes. What is the pi product stand? I just said it. The pi is for p, the p stands for product. So it's the same thing as sum. You're just, you're multiplying all of those together, okay? So this L of I term is defined by this product. These are called the Lagrange functions. Okay, so this is just the general form. And then I want you all to code it up. The example in the book codes this up for you. So I want you to code it up, and then it'll work for any number of data points. Okay, so product just means you're multiplying, summation just means you're adding them, right? Any questions about this? So once we have the Lagrange polynomials, I think we'll do the rest of this next week. We won't have time. But like I said, I really want you to review this because I think you're going to get tested on it. The linear splines, you're just getting the lines in between points. Quadratic splines, so the quadratic equation, right? Ax squared plus bx plus c. You're getting a quadratic between each of the points. And then finally, cubic splines. So it's just getting more and more and more complicated between each of those points. So we won't have time to do it this week, but just how we derive the equations with the math, certainly we can do that next week. All right, any questions? So once we do it for lines, we can do it for quadratics. Once we do it for quadratics, we can do it for cubics. And it just gets more complicated. And then therefore, it makes your data more and more accurate, makes your function more accurate. All right, that's pretty much it for the lab. I mean, for the discussion. So let's move on to the lab. So basically, you know, again, I try to be nice with the labs. So the fact that there's so much red makes me think that there's a typo somewhere. So I'll check that. We have the atmospheric pressure as a function of height. And then we have the data series. You want to calculate the slope, the y-intercept, and then pressure at 7,000. And then similarly for number 1, you have the data series, y is a function of x, same thing. So this one's already linear form. So go ahead and get started with that. I think you should start with 6.1. Some people are already getting that through. And then I'm going to stop recording. I'm going to see what's up with this one. Okay, any more questions? Thank you. I'm going to stop.